Hi folks, we're going to take a look at page 436, number 5, and I'm going to pick one of the combinations that's given, which is u being cos x and v being 0.95 to the x, and I'm going to pick the third one, which is v over u, so this function here. And what I'm going to do is I'm going to try to describe the function, because in trying to describe it, hopefully I'll be able to get enough information to draw a sketch of the graph. All right, so let's start with the domain here, and this is kind of nice because I'm dividing two functions that have domains of all real numbers. Okay, so I know I'm sort of starting with all real numbers, but I look at this denominator and I see that there's places where it's equal to 0. In fact, there's lots of places where it's equal to 0. So we have to exclude, okay, all those places where cos x is equal to 0. Now notice that if it was the other way around, cos x over 0.95 to the x, this function here doesn't have any zeros, okay? So we would have no restrictions. But in this case here, we definitely have some restrictions, and we just have to remember when cos x is equal to 0, cos x is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. So we can just say pi over 2 plus n pi, because every pi units, it's going to be equal to 0, okay, where n is, or such that n is an integer. Okay, so this is our domain. Now the question is what's happening at these points, or at these values where the denominator is equal to 0? Well, I know the numerator can never be equal to 0. So if the numerator is approaching some fixed number, when the denominator is approaching 0, I know I'm going to have vertical asymptotes there. So right off the bat, we can talk about our vertical asymptotes, okay, are going to occur at x equals, well, any of these places where the function is not defined. So pi over 2 plus n pi, where n can be any integer. Okay, so not surprisingly, we're going to have infinitely many of these. All right, so let's look at the x-intercepts. Okay, so since this is a quotient of two functions, I need to see where that numerator is equal to 0. And of course, we just talked about that. 0.95 to the x is never equal to 0, so there's no x-intercepts. All right, so let's start talking about the nitty-gritty of the function here. Okay, now we know n behavior is going to be a bit of an interesting one because of this cos x. But let's actually start seeing if we can graph and see if we can determine the behavior of this function. All right, so one thing I know is that there are definitely going to be some sort of periodic qualities to this function. Might not be a periodic function, but I know I'm going to have some ups and downs based on this cos x. So let's start by inputting some of these vertical asymptotes. Okay, so let's say this is pi over 2, or sorry, this would be negative pi over 2. Okay, and then we've got another vertical asymptote at pi over 2. Okay, and then 3 pi over 2. Okay, and then let's maybe put one more here. I guess this would be 5 pi over 2. All right, and what I'm going to do to help me sketch the graph here, wouldn't necessarily always do this. I don't want the graph to be too messy, but I think it will be helpful to try to put the initial functions in. All right, so let's say this is equal to 1, and this is equal to negative 1. So I'll put cos x in blue. Okay, so let's draw cos x. We know it's going to look like this. Okay, go up to 1, 0 at pi over 2, then eventually down to negative 1, back up to 0. Okay, and here's cos x, okay, a reasonable facsimile. And now let's put 0.95 to the x. So because the base has, it has a base less than 1, I know that it's going to be a decreasing function. And I also know that it's going to pass through 0, 1, okay, as all exponential functions do. So I know it's going to look something like this, you know. Because it's 0.95, because it's so close to 1, it's probably not going to decrease quite that quickly, okay? But just to give us a sense of what's going on. All right, so let's try to figure out how the function is going to behave, okay? And in fact, I'm going to start with one thing, is I notice that they're both equal to 1 here. And so wherever two functions are equal, well, I know that, I'm just going to have 1 divided by 1 at this location here. All right, so that means that the quotient is going to be equal to 1. So I know that it passes through this point here. Will also be on the combined function. And let's take a look at what's happening. Well, if I look at this asymptote here, I see that the numerator is approaching some fixed number, but the denominator is approaching 0 from the positive side. So I'm dividing some fixed number by some ever decreasing number. So I know I'm going to be going to positive infinity. And something similar here. The numerator is approaching some fixed number, but the denominator is approaching 0. So chances are I've got something that looks like this, okay, unless there's some funny squiggles going on, which I don't have the tools to figure out. It's going to look something like this in this region here. All right, so let's go to this next section. So first thing I notice that one of the functions is positive and one of the functions is negative. So I know it's going to have to live on the negative side. All right, so I have all these values here that are being divided by numbers, okay, because they're being divided by cos x by numbers that are between 0 and -1, okay? So if I take, say, this is 1/2 and I divide it by a half, what do I get? A half divided by a half is equal to 1, somewhere here. Half divided by a quarter is something, negative quarter is going to be something even further negative, okay? This is likely to be the point where I have the highest value, okay? So what I have is whatever this value is, okay, this would be just equal to pi. Whatever the y value is here, I'm dividing it by -1, okay? So let's see, this value is around there, so let's go to the negative version, -1, so it's probably going to be somewhere right around here, just the negative of whatever that y value is. And then what's going on? This is approaching 0 from the negative side as this is approaching some fixed number. So I'm going to be approaching -infinity. Similarly here, this is just approaching some positive number, whereas this is approaching 0 from the negative side. So I'm going to have something that looks like this. Okay? I hope you can start to see a pattern that here, the largest value I'm going to have now, the smallest value I'm going to have, because I'm taking these numbers here and I'm dividing them by cos x. Okay, the one that's going to have the smallest value is when I'm dividing by the largest number, which in this case here is 1. So whatever this value is, I'm just dividing it by 1. So hey, it's going to be right along that curve. And same thing for the asymptotes. Here, approaching some fixed number in the numerator, denominator approaching 0 from the positive side. So I'm going to have something that looks like this. Again, red function approaching some fixed number. The blue function, which is the denominator, is approaching 0 again from the positive side. So it's going to go to positive infinity. Okay, and if we go even further, if we try to draw one last branch here, okay, let's see what the red function's doing. Again, and what's cos x doing? So where is that local max going to happen here? Well, wherever this function is at the same location as where cosine has its minimum value of -1. So it's going to be whatever this value is, but now multiplied by -1, so somewhere on this side. So it's probably going to look something like this. And we start to see that we have all these branches, and we see that as we go to the right, they're getting ever closer to 0, and as we move to the left, they're getting ever further from 0. Okay, but not just that. It looks as though the trend is that these minimum values are following the numerator function, and these maximum values here seem to be approaching whatever the negatives of these are. So it's almost like we can draw a boundary on the upper and lower part. Now this video is about to end, so I'm going to end it here, and I'll do a part 2 in a second.